Okay, some baseball pitchers can go 100 miles an hour. So that's very few, very few. Okay, so 100 miles an hour is a very inconvenient unit. So 100 miles in 1 hour. I'm going to multiply that. Now here's what I'm going to do. You're allowed to multiply anything by 1. It doesn't change anything. So I can multiply it by 1 over 1. I can multiply it by 2 over 2. I want to multiply it by 1 mile equals 1,600 meters. That's another thing that's true. And then, hey, my 1's going to cancel out with my 1. My 2 is going to cancel out with my 2. My miles is going to cancel out with my miles. This is something you're allowed to do. It's called dimensional analysis. Some places call it stoichiometry. When you take chemistry, this becomes a very big deal. And I'll help you if you still need it. But now we're in meters per hour, which is almost what we need. Meters per second would be ideal. So I'm going to multiply it by 1 hour equals 60 minutes. 1 hour equals 60 minutes, so it's like we're multiplying by 1. We're allowed to do it. Then I'm going to multiply it by 1 minute equals 60 seconds. It's like multiplying by 3 over 3, 1 over 1. Lots of things we're allowed to do, but hey, the hour on top, going to cancel with hour on bottom. Minute on top, going to cancel with minute on bottom. We are left with meters per second, which is what we want. So now I'm going to type in my calculator 100 times 1,600 times nothing else times 1 divided by 60 divided by 60. And I got 44.4, like repeating, meters per second. Just to double check. Yeah. Okay, so that's the meters per second that baseball pitcher is pitching at. They achieved this by moving it that distance. What's the net force? Okay, what? So I know F equals ma. The net force, the sum of the force, has to be in the same direction as the acceleration. I think that wants to calculate the acceleration using kinematics. So with kinematics, there are 5 variables they can ask about. Initial velocity, I do O for original. You can do I for initial, doesn't matter. Final velocity, acceleration time, and change in displacement. I don't know a lot about baseball, but I think when we start a pitch, we start from rest, and then we like do things. So we start from rest. At the end of it, we're going 44.4 meters per second. The distance we go through is 1.5 meters, and we need the average force, which means we need the mass and the acceleration. They gave us the mass, so we need to calculate the acceleration. So we sure wish we knew that. Let's go through the Kinematics equation. So we have the square d1. We have delta x equals v naught t plus 1/2 at squared. I know I'm changing between vi and v naught. They mean the same thing. Apparently, I just change which ones I use all the time. And then we have vf equals v naught plus at. Okay. We don't have time, and we don't care about time, so we'll use the one without time, which is the square d1. That's the first one. So I'm going to say vf squared equals vi squared plus 2a delta x. The final is 44.4. We're going to square it. The initial is 0. We don't know the acceleration, but we sure wish we did. So 44.4 squared, 1975, equals 2 times 1.5. That's 3a. We divide both sides by 3. To get a by itself, a ends up being 658 meters per second squared. If that was an answer choice, it'd be a really tempting one, but it'd be a wrong one because we're not done. They asked for the force. You have to read the question really closely. So the force equals the mass, which is 0.15, times the acceleration, which is 658. So multiply that by times 0.15. I got my force is 98.8 newtons.